Hello! After I have shown you how I built a fan system for a cold forge in my last video, I will now take a closer look at the brushless DC motor that powers the server fan that I used. I will explain how normal brushed DC as well as brushless DC motors work, take a look at their driver circuitry and much more. But before I will talk about those two types of motors specifically, let us go over the most common types of electric motors found in consumer items, name them and see in which applications they are used. I do that because I'm sure that many of you are confused about the multitude of electric motors that they have seen while repairing devices or salvaging for parts. Here you see an overview of motors which I salvaged from household equipment over the last years. In the upper left corner we see an assortment of asynchronous motors or induction motors, as they are also called. This specific type of induction motor is called a shaded pole motor. It can be supplied with single-phase AC from a normal household electric outlet, but internally induction motors need to generate an additional phase shift, or a virtual second phase, as you could call it. The shaded pole motor does that by having so-called shading coils added to its magnetic core. The rotor of these motors is called a squirrel cage rotor. These shaded pole motors are so-called motor transformers. They simply have a secondary winding added to their magnetic core. This allows them to act as a transformer as well as a motor, a technique that was often used in tape recorders. The shaded pole motor is cheap, simple in build, reliable and long-lived, since it has no motor brushes. But on the other hand, it is very inefficient and thus only used for low-power applications. The shaded pole motor was widely used to drive phonographs and tape recorders. It can also often be found in microwave ovens, where it powers axial cooling fans. Another application are tangential fans in storage heaters. This tangential fan was salvaged from an overhead projector. The next type is the induction motor with motor capacitor. These induction motors use a squirrel cage rotor like the shaded pole motor. But they are different in that they have more windings. The phase shift, or virtual second phase, is generated by a capacitor that must be connected to the motor to drive it with single-phase AC from an electric outlet. The motors you see on this picture were salvaged from a dishwasher and a 1970s cassette player. The induction motor with motor capacitor is superior to the shaded pole motor in that it operates with higher efficiency. It is also long-lived because it has no motor brushes. Its efficiency and the generated torque are however inferior to the three-phase induction motor, as it can be seen on this picture of my drill press. Three-phase induction motors are robust, powerful, efficient and also very long-lived. They too don't need motor brushes, but, as the name says, they require three-phase AC, which is not available in every household. Therefore, they are rarely found in consumer products. With the advent of modern power electronics, however, it is now possible to build variable frequency drives that allow driving these motors from single-phase AC. I have no such motor lying on my bench because I never salvaged one. That's simply because you find them almost exclusively in industrial grade machines like my drill press. The next common motor type is the so-called universal motor. The universal motor is basically a slightly modified version of a separately excited DC motor that can be powered by DC as well as by AC, thus the name universal motor. Separately excited means that the stator or exciter field is generated by electromagnets and not by permanent magnets, as you might know it from small DC motors. But just like those DC motors, the rotor is electronically connected to the outside by a commutator with motor brushes. The universal motor can generate very high frequencies of revolution, and even a small unit can generate a lot of power. They are very versatile in that they can be powered with DC as well as with AC. Other than induction motors, they can easily be controlled by very simple phase-fired controller circuits, as you can see it in vacuum cleaners. You can even use a thyristor instead of a triac to build a very simple but effective variable frequency drive for these motors, as I will show you in a later video. The downside of these motors is, however, that they use a commutator which generates sparks and thus electromagnetic interference. The commutator also limits the maximum size of such a motor, as well as its lifespan. These motors can be found in vacuum cleaners and washing machines. They are also the typical motor used in power drills and angle grinders. Another, and maybe the best known of all, is the brushed DC motor. Its name indicates that it can be powered from DC directly, which makes it the most practical motor for battery-powered equipment. But internally, the DC motor, like all motors you see on my workbench, needs AC rather than DC to function properly. Therefore, it has a commutator, which acts as a mechanical inverter, supplying the windings of the rotor with AC. The motors you see here all use permanent magnets to generate the stator field. Large-scale DC motors, however, as they are used in industrial applications, often utilize exciter windings rather than permanent magnets. They look much more like the universal motors we saw before. Some of the advantages of the DC motor are its simplicity and its suitability for mobile applications. DC motors can also be controlled by very simple control circuits. Disadvantages of this motor type are again the brushes and the commutator, with their negative impact on electromagnetic compatibility and lifespan. Small DC motors can be found in printers, cheap CD drives, toy cars, cassette players and many other devices. Here you can see an assortment of different brushless DC motors, which will be the main topic of the latter part of this video. The BLDC, as it is also called, is basically a higher evolutionary step compared to the older brushed DC motor. As I will explain later, here the commutator was replaced by switching transistors. One of the most obvious features of the motors you see here is that the rotor is not spinning inside the stator windings, as it was the case with almost all motors we've seen before, but the rotor is actually mounted outside of those windings. You will find that this is almost always the case. It is, however, not a necessary requirement for a BLDC. It simply turned out to be more practical for this kind of motor. Brushless DC motors can often be found in CD and DVD drives and VCRs. This magnetic head from an old VCR has a brushless DC motor on its back. The little component here is a Hall effect sensor. Inside the head we find another curious component. It's a so-called rotary transformer. It has nothing to do with the BLDC, but we will have to talk about that in some other video. As I mentioned in the last video, brushless DC motors are also the most popular motors for small cooling fans like this one, but more about that later in the video. A last motor type that you can find in many modern applications is the stepper motor in its various shapes and forms. The stepper motor is actually a special kind of brushless DC motor, and watching this video will maybe also help you to understand stepper motors a bit better. But that topic is so complex that it exceeds the limits of this video. Stepper motors are long-lived. They have no commutator or brushes. Because they move in discrete steps, they can be controlled and operated reliably in open-loop systems, meaning that you need no additional sensors to know how many revolutions they make or at which angle they are. Their biggest downside, however, is that they always need rather complex driver circuitry to be operated. You can find them in printers and scanners, in many automotive applications and larger units even in industrial precision machinery. So I hope that this overview will help you find some orientation in the world of electric motors. Of course there are some other types like synchronous AC motors that I didn't mention, and of course there are various other subcategories and also alternative names for the motors I presented to you. But this assortment really gives you a good overview over the most common types in household equipment. Okay, so by now some people's heads are maybe already spinning around, because they were just overloaded with information. The sheer multitude of motor types and their different modes of operation can be very confusing, and I'm sure that some of you feel frightened by all those magnetic poles, windings, commutators and so on. But I will now try to give you some tools that will not only make you understand the DC motor and the BLDC, but that will help you understand the principle behind all electric motors that we have seen so far. For this I have set up a little experiment. It consists only of a compass, two solenoids with iron cores and a switch that I will hold in my hand. Now watch what happens with the compass needle. As you have seen, I was capable of getting the compass needle into a rotary movement. You may believe me at this point or not, but what I have just shown you is a rudimentary brushless DC motor. So what exactly is going on here? Here you see a drawing that I made of the setup. The compass needle is nothing else but just a magnetized piece of metal. In other words, a permanent magnet. This permanent magnet generates a magnetic field with magnetic flux lines, which will pass the space around the needle in this way. By the way, if you don't know what magnetic flux is, you should watch my SMPS tutorial part 5, where I explain some basics of magnetism. Over and under the compass we have two electromagnets which are connected to the switch and a voltage source in this manner. By activating the switch, one of the solenoids is turned on, while the other one is turned off. Current is starting to flow through one of the solenoids, which builds up a magnetic field around it. According to the right-hand rule, the direction of the magnetic flux generated by the solenoid will point roughly in this direction. Now, the two magnetic fields will try to align with one another. Therefore, a force F, or actually a torque M, is applied to the magnetic needle of the compass. The needle will keep moving until the fields have aligned. Now I activate the switch again, turning the other electromagnet on, which results in a reversion of the stationary magnetic field, which we will call the stator field from now on. This will again force the magnetic needle to move, trying to realign its own field, which we will call rotor field, with the stator field. And the magnetic needle will keep on going in the same direction, because it has a mass and thus a moment of inertia, meaning that it already has a momentum towards one direction. It will keep that direction when the switching action is timed correctly. If you would now replace the manual switch by switching transistors and activate them with a Hall effect sensor rather than with my hand, you would have a true brushless DC motor. Now of course, a brushless DC motor is built up a bit differently in real life, but as you will see, the principle is identical. From this experiment and our former lessons, I want you to keep the following in mind. Lesson 1. The underlying principle of electric motors is the phenomenon that two magnetic fields which exist inside the same space try to align with each other. When one of the fields is stationary, meaning fixed in space, while the other one is free to move, a kinetic force is applied to the magnetized piece of matter that generates the free field. That force is trying to align the two magnetic fields. A popular application, the compass. Lesson 2. In the case of electric motors, it doesn't matter if the rotor is permanently magnetized or magnetized by current flowing through a winding. It is, however, always necessary that at least one of the two elements, rotor or stator, is magnetized by an electromagnet, because otherwise you wouldn't have the possibility to reverse the direction of one of the fields periodically. Therefore, the following permutations are possible. The rotor can be magnetized by an electromagnet, while the stator is also magnetized by an electromagnet. Applications are the induction motor and the universal motor. The small-scale DC motors, which we saw before in the video, fulfill the conditions of line 2, where the rotor is magnetized by an electromagnet, while the stator is magnetized by permanent magnets. In line 3, the rotor is a permanent magnet, while the stator is an electromagnet. This is true in the BLDC, or most of them at least, and with stepper motors. The permutation in line 4 cannot be utilized to build a motor, and I don't care what any of the free energy idiots is telling me. It is not possible. Okay, for the stuff that follows now, I also want you to remember these facts. Earth's magnetic north pole is actually a magnetic south pole. That means that the tip of a compass is attracted by magnetic south poles. Second, a magnetic north pole is the location where magnetic flux lines exit a magnet, while a south pole is there where the flux lines enter the magnet. Third, the magnetic field lines are always closed loops. And fourth, the magnetic flux prefers the path of lowest magnetic reluctance. Now, with this knowledge, we can tear down a DC motor and a BLDC, look what's inside and analyze what we find. What you see here are the motor brushes. This is the commutator, and this is the rotor, which has 3 poles. And with the DC motor, it is called armature. The dark ring that you see here is the stator, which is actually a ring-shaped permanent magnet. Now, you might have seen 2-pole DC motors in school, but actually all real-life DC motors have at least 3 poles, as you will see when you tear down some of your own. The next thing that I do now is to pull out the stator magnet out of the motor's casing and try to determine how this ring-shaped magnet is actually magnetized. I do this with the help of a compass needle. Here we have a north pole . And here we have a south pole. We label the 2 poles with little stickers so that we know where they are. With this knowledge, we can now try to determine how this brushed DC motor actually works. Since the stator has only 1 north pole and 1 south pole, the field generated by the permanent magnet would look like this. You have also to consider that what we measured as north and south poles outside the ring are actually a south pole and a north pole inside the ring. So you already see why I'm urging you not to think in terms of attracting and repelling poles as they taught you in school, but to think in terms of magnetic fields that want to align with each other. When the rotor is introduced into the stator field, new, lower reluctance paths are provided so that the biggest portion of the flux will bend and wander through the rotor rather than through the air, which has much lower magnetic permeability than the silicon steel of the rotor. When now a current starts to flow via the commutator into the windings, a second magnetic field is building up around the rotor. Since the 3 coils of this motor are connected in a triangle, current will flow through all 3 windings. But because the current through that winding, which is momentarily connected directly to the source, a higher current is flowing than through the other windings, which are effectively connected in series. Therefore, the magnetic flux of that winding will overpower the other fluxes, and the rotor will shape either 1 north and 2 south poles, or 1 south and 2 north poles. As with the example with the compass needle we saw before, the stator field and the rotor field will now try to realign, applying a torque on the rotor. Once the motor is realigned, the rotor field will change its direction via the switching action of the commutator. And this will go on so that the motor keeps spinning. But enough of this, since we actually want to look at BLDCs here and not at normal brushed DC motors. For that, I show you how you can easily take a look at a BLDC yourself. You simply take an old PC fan like this one. You first remove the label, and then, at least with cheap ones like this, you also have to remove a little plastic ring from the rotor shaft. Now you can simply pull off the rotor from the stator. Next, I removed the wings from the rotor to determine its magnetization, just as I did it with the brushed DC motor before. As you can see, the result this time is that the ring-shaped permanent magnet has not 2, but 4 poles. That means that the magnetic field lines have to travel roughly in this way. This specific type is a two-phase BLDC, and it is a type commonly used in PC fans. It has, as you can see, 4 poles, but each limb of the magnetic core actually carries not one but 2 windings. The 2 windings are, as in this picture, wound with a reversed winding sense, so that the current through them will generate magnetic fields of opposing direction. In many real BLDCs, the 2 windings have the same winding sense, but then the windings are connected in such a way that the current flow through them will be opposed, which has the same outcome. The 2 windings are then connected together at one end and attached to the plus pole of a voltage source, while they are connected to ground via 2 electronic switches. First, one switch is closed so that current flows through the first winding, generating a stator field that is opposed in direction with respect to the rotor field. Now the 2 fields try to align and the rotor starts spinning. Once the fields are nearly aligned, the first switch is opened and the second switch closed, forcing current through the second winding, reversing the stator field so that the rotor will spin on to align with the stator field. The stator field is then periodically reversed, and the switching action is timed by a Hall effect sensor that can detect a magnetic pole passing by. So, this is basically the principle behind brushless DC motors. In reality, the switches are most of the time MOSFETs, either integrated in an IC or discrete ones for higher currents. The Hall effect sensor can be integrated or discrete as well. There are also lots of BLDCs with more phases and much more poles, but the principle is the same. And we will talk about these more practical aspects of BLDCs in a third part that I will make since this video is already too long. In that part I will then finally come to the driver circuits, the reverse engineer circuit of the server fan, the PWM controller, and of course I will show you how I implemented all that for my cold forge. So I'll call it a day and see you soon.